electronic lead and lag compensators. Hello everyone, in this video we're going to review the concepts of lead and lag compensation, so some exercises, and afterwards implement an electronic lead compensator using 4 resistors, 2 capacitors and 2 operational amplifiers. That's it. Let's do it. Consider the structure that I drew on the board. It is an electronic lead or lag compensator. Observe that Z1 is the parallel connection between resistor R1 and capacitor C1. Observe also that Z2 is the parallel connection between resistor R2 and capacitor C2. The resistor is represented in the complex domain by the resistance, here R1 and here R2. The capacitors are represented in the complex domain by their reactances. Okay? Here 1 over S C1 and here 1 over S C2. Okay? Then Z1 of S is equal to the parallel connection between resistor R1 and capacitor C1. And Z2 is the parallel connection between resistor R2 and capacitor C2. Alright? Then Z2 of S over Z1 of S will be equal to R2 over R1, R1 C1S plus 1, R2 C2S plus 1. This is Z2 over Z1, which can be rewritten as C1 over C2 S plus 1 over R1 C1 over S plus 1 over R2 C2. Okay? With this result, we can write the global transfer function from the output to the input in the complex domain. Then the global transfer function is going to be E0 of S over EI of S, which is going to be Z2 of S over Z1 of S times R4 over R3. And we are going to substitute this and this here to get the global transfer function, which can either be R2, R4 over R1, R3 multiplying R1, C1 S plus 1, R2, C2 S plus 1, or if you prefer, R4, C1 over R3, C2 multiplying S plus 1 over R1, C1 over S plus 1 over R2, C2. Okay? This is the global transfer function correlating the output and the input in the complex domain. Remember that Z2 is the parallel connection between resistor R2 and capacitor C2, and Z1 is the parallel connection between resistor R1 and capacitor C1. Okay, we are going to see some concepts here that electrical engineers and electronics engineers like to work with, and we are going to see when this is a lead compensator and when this is a lag compensator. Let's go. The transfer function again is of the sort E0 of S over EI of S. And we are going to use a constant here called Kc, which is the gain of the compensator, multiplying alpha, which is another constant, and here Ts plus 1 over alpha Ts plus 1, which is equal to Kc S plus 1 over T over S plus 1 over alpha T. Okay? Where T is equal to R1 C1. Just compare this and this with the transfer function that I drew before this, that I just erased. Alpha T is equal to R2 C2, and Kc is equal to R4 C1 over R3 C2. Okay? With this, we notice that alpha is equal to R2 C2 divided by R1 C1. And alpha is called the attenuation factor. Okay? The attenuation factor. And Kc times alpha, this Kc times alpha, which is equal to R2 R4 divided by R1 R3, is the DC gain. Okay? This is the DC gain of the compensator. And when does it function as a lead compensator, and when does it function as a lag compensator? When alpha is greater than 1, this is a lag compensator. And when alpha is less than 1, this is a lead compensator. Okay? These are the characteristics of the lead and the lag network. Now, after this, let's see the concepts of a phase lead of a lead compensator. Okay? Consider a lead compensator having the following transfer function. Now we are going to work with a lead compensator only. The transfer function is Kc alpha Ts plus 1 over alpha Ts plus 1, which can also be written as Kc S plus 1 over T over S plus 1 over alpha T. Okay, this is the transfer function of the lead compensator. Here for alpha, between 0 and 1. We want to know the maximum phase lead of this compensator. The maximum phase lead is this angle here. We want to know the maximum phase lead provided by this compensator. The maximum phase lead is, by definition, the inverse sine of 1 minus alpha over 1 plus alpha. Okay? This is the maximum phase lead. And Wm is the frequency at which the maximum phase shift occurs. Okay? We are calculating the maximum phase lead or the maximum phase shift provided by the lead compensator. And the maximum phase shift or maximum phase lead is this angle here, which is the inverse sine of 1 minus alpha divided by 1 plus alpha. And the frequency at which this occurs is 1 over the square root of 2 times t. Sorry, the square root of alpha times t. Okay? Not 2, this is alpha. The square root of alpha times t. Okay? Now let's go to the exercises. We are going to solve one exercise here that involves all these concepts about phase shift, okay, provided by the phase lead compensator. Okay. The exercise, what is the maximum phase shift a lead compensator represented by the transfer function would provide? The transfer function is Gc of S equal to 10 times 1 plus 0.3 S over 1 plus 0.1 S. Okay? What is the maximum phase shift a lead compensator represented by the transfer function would provide? A general compensator transfer function is of the sort as I wrote here, Kc times alpha Ts plus 1 over alpha Ts plus 1, okay? In this exercise, if you compare one with the other, you're going to see that T is equal to 0.3, okay? Here, T is 0.3, and alpha T 0.1, alpha T 0.1, therefore, alpha is equal to a third. With this value of alpha, we can calculate the maximum phase shift, which is m is equal to the inverse sine of 1 minus a third divided by 1 plus a third, which is equal to 30 degrees. This is the maximum phase shift this lead compensator would provide. Now let's solve another exercise which is similar to this, and this exercise will involve the frequency at which this occurs. Let's see another exercise that discusses this concept of maximum phase shift provided by a lead compensator. Okay? All right. The transfer function is GC of S equal to 0.5 plus 1 over 0.05 S plus 1. Okay? The question is, what is the maximum phase shift a lead compensator represented by the transfer function 0.5 times S plus 1 divided by 0.05 S plus 1? Okay, again, we are going to use the transfer function of a general compensator, which is Kc times alpha Ts plus 1 divided by alpha Ts plus 1. Okay? And here we see that it's 1 multiplying here. Then Kc times alpha is equal to 1. Alright? We see that T is equal to 0.5. Okay? T is equal to 0.5, and we see that alpha T is equal to 0.05. Alpha T is equal to 0.05. Okay, therefore alpha is equal to 0.1. We divided this by this and we get 0.1. Alright? Now we are going to calculate the maximum phase shift, and the maximum phase shift is equal to the inverse sine of 1 minus alpha divided by 1 plus alpha, which is 1 minus 0.1 divided by 1 plus 0.1. And if we take the inverse sine of this, we get 55 degrees. 55 degrees. Okay? And the frequency at which this angle occurs is Wm equal to, as we said before, the frequency at which is 1 over T times the square root of alpha, and then here we get that it is 1 over 0.5, T is 0.5 times the square root of 0.1, which is the square root of alpha, and this is 6.32 radians per second. Okay, my friends? This is exercise 2, talking about the maximum phase shift of a phase lead compensator. Now let's go to exercise 3. Exercise 3 is a little bit more difficult. I'm going to have to erase it all here to draw what the exercise wants us to draw. Okay? Let's go then to exercise number 3. Now let's go to exercise 3. Exercise 3 wants us to consider the system represented by this block diagram. It is desired to modify the closed loop poles so that an undamped natural frequency Wn equal to 4 radians per second is obtained without changing the value of the damping ratio. This is what we are going to do. We are going to compensate this system here so the undamped natural frequency is 4 radians per second. Okay, my friends, let's go to the solution. Observe that a general second order system can be modeled by this block diagram. Okay, we are going to use this to understand what's going to be done here for this. Okay, Wn squared is 4. Okay, Wn squared is equal to 4. Consequently, Wn is 2 radians per second. The uncompensated system has the undamped natural frequency equal to 2 radians per second. We want 4 radians per second without changing the damping ratio. Okay? Observe that 2 times zeta times Wn is equal to 2, okay? 2 times zeta times Wn is equal to 2, which gives a value of 0.5 for zeta. Alright? The closed loop transfer function is C of S over R of S is equal to 4 over S squared plus 2 times S plus 4. And if we solve this for S, we get the closed loop poles of the uncompensated system, which is the closed loop poles are -1 plus minus j square root of 3. Then the transfer function is of the sort 4 over s plus 1 plus j square root of 3 s plus 1 minus j square root of 3. Okay? This is the uncompensated system. And the root-locus plot of the system is going to be, we have here the imaginary axis and here the real axis. Here is sigma, here is JW. Remember that this is the complex plane where S is equal to sigma plus JW. Okay? And the root locus is going to be, we have a pole at 0. Okay? We have a pole at 0 and we have a pole, open loop pole at -2. Okay? -2. And this is part of the root locus, and we have a root locus here, -1 here, and this is the root locus plot of the system from 0 to -2, and this line here, okay? And the closed loop poles will be j square root of 3, -j square root of 3, okay? -1 plus j square root of 3 here, alright? And the -1 minus j square root of 3 here. Okay, these are the closed loop poles. And observe that for the damping ratio of 0.5, we have an angle here. We have an angle here of 60 degrees, okay, plus minus 60 degrees. The damping ratio of 0.5 requires that the complex conjugate poles lie on lines that make plus minus 60 degrees with the negative real axis, okay? The damping ratio gives the angular location of the closed loop poles, and the Wn, the distance from the origin. Okay? The damping ratio gives the angular location, and the undamped natural frequency gives the distance from the origin. Alright? Here and here. Okay. But this is not the desired location of the pole. Okay? We have a closed loop pole at minus 1 plus j square root of 3 and minus 1 minus j square root of 3. This is not the desired location of the pole. What is then the desired location of the pole? The desired location is going to be S equal to minus zeta Wn plus minus jwd. Okay? Where S has to be equal to minus 2 plus minus j2 times the square root of 3. In this way, zeta, or the damping ratio, is preserved. We're going to have a zeta here equal to 0.5 as we wish. And since this is this, okay, negative zeta Wn is equal to negative 2, then we're going to have Wn equal to 4 radians per second, okay? This is what we wish. We don't have it yet. This is what we wish. Then we will need to compensate the system, all right? We are going to use a lead compensator. If gain adjustment alone does not move the closed loop poles to the desired locations, a lead compensator may be inserted in the feed-forward path. We are going now to design a lead compensator that will move the closed loop poles to the desired locations. Alright? This is the reason for using compensator. Alright, let's do it now. Let's use the compensator. We had a pole at, for example, one of the poles, we had a pole at negative 1 plus j square root of 3. We have this. We want a pole at, for example, one of the poles, 2 plus j times 2 square root of 3. This is what we have, and this is what we want. We are going to use a compensator to have this, what we want. Okay? Okay, now let's go over the procedures for the design of the lead compensator. First of all, find the sum of the angles at the desired location of one of the dominant closed loop poles with the open loop poles and zeros of the original system, and determine the necessary angle phi to be added so that the total sum of the angles is plus minus the total sum of the angles has to be equal to plus minus 180 degrees to k plus 1, okay? The lead compensator will contribute with the angle phi. We are going to have the sum of the angles, and it will not give 180 degrees, plus minus 180 degrees to k plus 1. But when we add the angle provided by the lead compensator, this sum, the sum of angles, has to be equal to plus minus 180 degrees to k plus 1. All right? Then let's go over the open loop transfer function of the compensator. The compensated system, GC of S, G of S. G of S is this, the transfer function or the block diagram of the original system, and this is the block diagram of the compensator. Together, they are the block diagram of the compensated system. Okay, the open loop of the compensated system is this. Okay, and it is of the sort Kc S plus 1 over T over S plus 1 over alpha T. All right? And this is the transfer function of the compensator, and we are going to multiply it with the transfer function of the plant. All right? Therefore, we're going to get that GC, this is the transfer function of the compensator, and this is the transfer function of the plant. Together, they are the transfer function, or the open loop transfer function of the compensated system. This is not the closed loop transfer function. This is the open loop transfer function of the compensated system, where GC of S is equal to Kc times alpha Ts plus 1 over alpha Ts plus 1, which is also equal to Kc S plus 1 over T S plus 1 over alpha T, for alpha between 0 and 1. When alpha is between 0 and 1, this works as a lead compensator. When alpha is greater than 1, this network works as a lag compensator. All right? Now, let's go over the procedures. This is one of the steps. Let's go and see the other step in designing this lead compensator that's going to compensate the system so the closed loop poles will be at the desired location. Okay, the next step is to determine the locations of the zero and the pole of the lead compensator. We'll choose the largest value of alpha for optimal system performance. First of all, draw a horizontal line passing through P, the desired location of one of the dominant closed loop poles. We're going to have here the complex plane again, alpha JW. Then we have here the desired location of the pole. We're going to draw a horizontal line here like this, A. And now we are going to draw a line connecting the point P to the origin, okay? And we are going to bisect the angle between PA and PO. We're going to bisect this angle here, okay? And it's going to be like this, and this is going to be B, all right? And draw two lines, or PC and PD, that make angles phi over 2 with the real axis. Here, PD, and here, PC. Okay? Here is D, here is C, and these angles here are phi over 2 and phi over 2. Okay, remember that the angle phi is the angle that the compensator will contribute with the system so that the angle condition is satisfied. Alright, here we're gonna have a 0, and here we're gonna have a pole. Okay, this 0 here and this pole here, the 0 is minus 1 over t, and the pole is minus 1 over alpha t, okay? In the present system, the angle of G of S at the desired location is, so these are the desired locations, okay? And from this we discover the angle. In this present system, the angle of G of S at the desired location of the closed loop pole is the angle of 4 over S plus 2, this angle at S equal to negative 2 plus J square root of 3. This is what we wish, okay? We want this. The angle is 210 degrees, okay? 210 degrees. Thus, if we need to force the root locus to go through the desired closed loop pole, the lead compensator must contribute with the angle of, this is negative, the angle of 30 degrees, okay? We wish plus minus 180 degrees. But the sum of angles are minus 210 degrees plus the angle of the compensator. The angle of the compensator here has to be 30 degrees, okay? With 30 degrees, we add 30 degrees minus 210 degrees, and we get negative 180 degrees, and then the system is successfully compensated. Okay, let's continue. Let's continue seeing how to compensate a system zero and pole of the lead compensator, zero and pole of the lead compensator, 0 at S equal to minus 2.9, and pole at S equal to minus 4.5. Okay? These are the locations that we found by bisecting the lines, by drawing the this figure that I just drew here, connecting the point to a horizontal line, to the origin, and when we do this, we find these values here, okay? And with these values, we are going to have values for alpha and for t. T is going to be 1 over 2.9, which is equal to 0.345, and alpha t equal to 1 over 5.4, which is 0.185. In this way, we discovered that the attenuation factor is 0.537, the value of alpha. Okay? This is important because we want alpha to be between 0 and 1. Alpha, for this to be a lead compensator. Alpha greater than 1, this is a lag compensator. The open loop transfer function of the compensated system then becomes, okay, the compensated system is GC of S times G of S equal to KC S plus 2.9 over S plus 5.4. Okay, this is the compensator, and this is the plant. The plant, as we saw, is for S plus 2, okay, which can be rewritten as K S plus 2.9 divided by S plus 2, S plus 5.4, okay, and where K is equal to 4 times Kc. K is equal to 4 times Kc, okay? Now let's draw the root-locus plot of the compensated system. With this we can draw the root-locus plot of the compensated system. Okay, the next step is to draw the root-locus plot of the compensated system. We're going to have here JW, sigma, the complex plane. As we saw, we have root-locus here from the origin 0 to -2, -2, and we have a 0 here at -2.9, and we have here another pole at -5.4, okay, and we're gonna make the root-locus pass here and here, and it's gonna bend like this, okay? This is the root-locus plot of the compensated system. And here we have angles. Here we have angles. Here -4. -15 degrees. Remember that we said that the compensator would need to contribute with 30 degrees. The angle would be 30 degrees. And here we have phi over 2, which is 15 degrees, and phi over 2, which is also 15 degrees. And we have root-locus here, and we have root-locus here too. Okay, This is the root-locus plot from 0 to -2 and from -2.9 to -5.4, and this line here, okay, this is the root-locus plot of the compensated system. Now let's talk about the gain, okay. The gain can be evaluated from the magnitude condition K or S plus 2.9 S plus 2, S plus 5.4. The magnitude of this has to be equal to 1 at S equal to -4 plus J 2 times the square root of 3. Then the gain is equal to 18.7. The gain is then 18.7. Okay? And the compensated transfer function is GC of S. G of S is equal to 18.7 S plus 2.9 divided by S plus 2, S plus 5.4. Okay? Where alpha, as we know, alpha is equal to 0.537 and Kc equal to 4.68 and Kc times alpha equal to 2.51. Okay, we're going to use these values to find the transfer function of the lead compensator. The lead compensator has a transfer function, okay? Now, the transfer function of the lead compensator, the electronic circuit that's going to force the root-locus plot to pass at the desired location to be GC of S is going to be 2.51, 0.345 S plus 1 divided by 0.18, 5 S plus 1, which is also written as 4.68 S plus 2.9 over S plus 5.4. Okay, this is the transfer function, the open loop, not the closed loop. This is the open loop transfer function of the compensator that we are going to use. Okay, we are going to use these values here to calculate the resistances and the capacitances of the electronic lead compensator that we are going to use to compensate the original system so it meets the requirements. Okay? And this is the general structure of a lead compensator using operational amplifiers, resistors, and capacitors. Observe that the transfer function of a general compensator is E0 of S over EI of S, which is R2, R4 over R1, R3 multiplying R1, C1, S plus 1, R2, C2, S plus 1. Okay? And here, specifically in this exercise, we discovered that R2, R4 over R1, R3 is 2.51, which multiplies 0.34 5s plus 1 divided by 0.18 5s plus 1. Okay, so this term R2 R4 over R1 R3 has to be equal to 2.51 and R1 C1 equal to 0.345 and R2 C2 equal to 0.185. Okay, in this way, with these values here, we will force the root-locus plot of the compensated system to pass at the desired closed-loop poles. Okay, my friends? This is how we do it, how we implement a lead compensator. With these results here, with these values of the resistances and the capacitances, using operational amplifiers, we will force the root-locus to pass at the desired closed-loop poles, and the system will behave in accordance with what we wish it to behave, and thus meet specifications. Okay? Alright, my friends, this is the video that I wanted to make. I hope you guys enjoyed it and learned from it. I am a teacher. If you want to book a lesson with me, use my WhatsApp number, guys. Goodbye!